All right, let's look at our work and energy homework. For number one, you're supposed to identify the energy conversion that's happening. These are kind of tricky because most interactions involve many kinds of energy, but the best way to do it is to first think about what kind of energy do you start with, and then what kind of energy is the system gaining as time goes by. Don't just look at what it has at different points along the way, but what is it actually gaining? So let's just try A. A person is lifting a box. That means they're taking it from here and lifting it up in the air. So it's true that it has to move going upwards, getting kinetic energy, but it's not going faster and faster and faster. What it's really gaining as it goes up in the air is gravitational potential energy. So let's do this. Let's take potential energy, gravitational potential energy, and we'll put it here. It's gaining potential energy. What did it start with? The person had in their body chemical potential energy. So basically, when you lift a box, you're converting chemical potential energy in your body into the gravitational potential energy of the box. Let's put these back and try again. Alright. Now, in the next one we have a mousetrap is snapping. Well, before the mousetrap snaps, what type of energy does it possess? It's a wound up spring, so therefore it has mechanical potential energy in a stretched material or compressed material. And when it snaps, it's definitely going faster and faster and faster. Therefore, what it is gaining is kinetic energy. Now, let's try the next one. A car is accelerating. That means it's going to go faster and faster and faster. So since it's going faster and faster and faster and faster, what it's gaining, therefore, is kinetic energy. Where did the energy come from? Well, it was in the gas tank in the form of a chemical called gasoline, so therefore it has chemical potential energy. Alright, let's try number D. Okay, a windmill is charging a battery. So let's just look at the windmill. So I have a blade of a fan that is spinning around. The energy it possesses by virtue of spinning around is kinetic energy. Now it is true that we're pushing electricity through wires, so it would be electrical energy, but what we're doing in this case is we're charging a battery, and a battery stores that energy as chemical potential energy. Alright, let's move on to D. An apple is ripening. And it looks like I left off a form of energy, so let's go ahead and write it in. It's coming in as light energy. Sorry about that. And it's being stored in the sugars of the apple, so therefore it is ending up as chemical energy. Okay, so now let's look at number 2. What we have here is a sumo wrestler, and this sumo wrestler weighs 2440 newtons. Remember, newtons measures force. And this wrestler is going to do 10,980 joules worth of work. So that is work. And what we're asked to find for this wrestler is how high up the platform. I always suggest look for the word, the interrogative word that makes it a question, and see what your variable trying to solve for is how high. So we're going to use the work equation. Work equals force times distance, and we're going to be solving this one for distance. So let's just substitute in the values that we know. We know that the work in this case is 10,980 joules worth of work was done, and the force needed to lift the sumo wrestler was 2440 times distance. Now, to get this by itself, what I have to do is I have to undo what's being done to distance. So distance is being multiplied by this, so I'm going to do the opposite of multiply. I'm going to divide this side by 2440 newtons, and I'm going to have to divide this side by the same thing in order to keep it equals. And therefore, what I find is 4.5 meters. Now, for number 3, we're asked that if the sumo wrestler in this example above has a mass of this many kilograms, how fast? So the question we're looking for is how fast. Fast is velocity. We're looking for velocity. Kilograms that we have here measures mass. And we know what equation we'll have to use then. The equation we'll have to use is the kinetic energy equation, which is kinetic energy equals 1/2 the mass times the velocity squared. So sometimes students get confused with this. They go, wait a second, you didn't tell me what the kinetic energy is. But I don't have to tell you what the kinetic energy is, and here's why. Energy is energy is energy, and what we see is up here that the amount of work done by this sumo wrestler was 10,980 joules. So although in this example here that was potential energy, in this one down here it's going to be kinetic energy. So I'm simply going to take this value and I'm going to put it down here. So 10,980. So I'm going to go ahead and say 10,980 joules equals 1/2 of his mass, which is 244, times velocity squared. Now, half of 244 is 122 times v squared equals 10,980. I'm not going to write my units just now. Now let's see what we have to do. We have to undo what's being done to our variable v. Right now, v is being multiplied by 122, so the opposite is to divide by 122. So I'm going to divide both sides by 122, and when I do that, that tells me that v squared equals 10,980 over 122. So that tells me then that 90 equals v squared, but I don't want to know what v squared is. I have to undo squaring v, and the opposite of squaring is taking the square root. So I'm going to take the square root of v squared to find out what v is, but that means I have to take the square root of 90, and what that tells me then is v equals the square root of 90, which is 9.4868 meters per second. And it looks to me like what I've got here is 3 significant figures. So I'm going to go ahead and round it for significant figures, and I'm going to say that v equals 9.49 meters per second. Okay, now in number 4, let's see what we're trying to find out. A woman lifts we know the force, we know the distance, and we know the time. So let's see, what kind of energy did she give the bowling ball? Well, by taking it from one position and lifting it to a higher position, what you're giving it is gravitational potential energy. How much energy did she give the bowling ball? Well, to calculate that, I'm going to use the work equation. Work equals force times distance. And in this case, I'm looking for work, which is force. The weight of the bowling ball, which is 78 newtons. That's the amount of force that would have to be applied. So 78 newtons times, in this case, the height that she lifted it was 1.8 meters of distance. And what that gives me is the amount of work is 140.4 joules. And it looks like what I have here is 2 significant figures. So I'm going to round my answer to 2 significant figures, and therefore I'm going to say the work that she did is 140 joules. Now, how much work did she do during the 5 minutes she held it over her head? Well, in this case, when she held it over her head, she was applying 78 newtons of force, but she moved the bowling ball a distance of 0 meters in that time. And therefore, although it feels like she's doing work, she's not giving the ball any energy. So what we have to say then is she did 0 joules of work on the bowling ball. It's a weird way of saying it, but that's how we say it. Moving on to number 5, okay. In this case, let's look what we're trying to find here. I'm just going to skip through and find the interrogative word. How fast could it possibly fire? So what we are looking for in this case is we are looking for velocity, and that means we have to use the equation that says kinetic energy equals 1/2 mv squared. In this case, we're looking for the v, so I'm going to substitute in the values I know. What I have is joules measures energy regardless of what type, so I'm going to put that over here. 5,900, I'll leave off the j's for right now, equals 1/2 of the mass, and the mass is a mere 0.05 equals v squared. Now I'm going to take half of 0.05, that's 0.025 times v squared equals 5900. Now I have to undo what's being done to v. It's being multiplied by 0.025, so I'm going to divide both sides by 0.025, and that means this went away. But now I'm still left with the fact that this is solving for v squared, and I don't want to know what v squared is, I want to know what v is, so I had to take the square root of both sides. So I'm just going to take my calculator and I'm just going to say square root 5900 divided by 0.025. And when I do that, what I'll find is the v equals 485.798 meters per second. Well, in this case, what have I got? Sadly, in this case, what I've got is simply one significant figure. So I'm just going to go ahead and round all of this. I'm simply going to round it and say, it's about 500 meters per second equals the velocity. Okay, now number 6 is a little bit trickier than the ones we've been doing. Let's see why that is. Okay, we're asked to find how high it will go, which means we need to use the work equation. However, in order to use the work equation, work equals force times distance. Since I'm looking for distance, I have to know what the amount of work is and the amount of force. Now, I wasn't given either of those values, but I'm going to have to calculate them. So let's start off by calculating how much work was done. Remember, work is measured in joules, and what I know here is meters per second measures velocity. So I'm going to have to use the kinetic energy equation to begin with. So I'm going to say kinetic energy equals 1/2 mv squared, and therefore I have half the mass of the arrow, which is 0.22, times the square of the velocity, which is 66 squared, and let's just see what that equals. And that gives me a kinetic energy of 479 joules. So I'm going to take this value here and I'm going to put it up here. So let's try this. Then I have 479 equals, now I've got to be careful, here's why units are everything. Force is measured in newtons, and what I was given was the mass in kilograms, but I was told, don't forget, 1 kilogram on Earth at least equals roughly 10 newtons, so therefore I'm simply going to convert. So let's just see how I do that. To convert, I'm going to say 0.22 kilograms, put kilograms in the basement, put newtons up above, 10 of these equals 1 of these, therefore this arrow is 2.2 newtons. I'm now going to take that value and substitute it up here, 2.2 newtons, times distance. Now I have to undo what's being done. I'm multiplying by 2.2, so I'm going to divide both sides by 2.2. And what I'll find then is, sorry for the mess here, is 217.8 meters, but it looks to me like I have two significant figures here, so I'm going to round my answer to two significant figures. Remember, we're not going to let our conversion factors limit our significance, so I'm going to round that to two significant figures. In that case, it's 220. So the answer is 220 meters equals the distance in the air that arrow can be fired. Now for number 7, let's see what we're trying to find. In this case, the question is how much force was required to pull the string. So we're going to be using the work equation. Work equals force times distance. Now, I know the distance. It's right here. So I can say that the force is what I'm looking for. And I know the distance is 0.76 meters. The question now is how much work is done, but if you recall, to find work is just energy, and what I know here from the last one I did is the kinetic energy, and I'm sorry it's a mess, but the kinetic energy was 479 joules. So I'm going to take this value, 479 joules, that I got from using the kinetic energy equation above, and that's what I'm going to put down here. 479 joules equals force times 0.76 meters. So now I've got to get force by itself. That means I have to undo what's being done to it. It's being multiplied by 0.76. So I'm going to divide both sides by 0.76 meters. Whoops. 0.76 meters. And that means the force equals, it equals 630 newtons. Alright, let's look at number 8. In this case, I have 155 kilograms. That's mass. Cart is pushed with, here's force, here's meters. Now let's look at what I'm asked to find. If all the work went into kinetic energy, how fast would it go? So I'm looking for velocity. I have to use the kinetic energy equation. So I know I have to use the equation kinetic energy equals 1/2 mv squared. Now, in this case, I haven't been told what the kinetic energy is. I'm looking for velocity. I know that the mass is 155. So I'll go ahead and say 1/2 of 155 times v squared equals the kinetic energy. But darn it, Mr. Simpson didn't tell you the kinetic energy, but that's okay. You can figure it out using this information here. We're going to use the work equation here. We're going to say work equals force times distance. In this case, work equals 450 times 15, which equals 6750 joules. So I'm going to take that value here. That's how much energy went into it, and it can take any form it wants. In this case, it's going to take the form of kinetic energy. So even though I use the work equation, I'm going to substitute that value of joules for kinetic energy. So I'm going to write 6750. Now you know what? We've solved a bunch of these. I think you know how to do this. When all is said and done, once I've done this, what I'm going to find is the velocity is 9.3 meters per second. But if I look at the next one, it says, but if the cart only ended up going this fast, which is significantly slower than this, how much of the work is being converted to heat through friction? So I want to find out how much energy is missing in this case. So I know I have this much energy to begin with. Now what I'm going to do is I'm going to calculate the amount of energy that's present here, and the difference between that and this is what I've lost to heat. So I'm going to once again use the kinetic energy equation. In this case, I'm going to say that kinetic energy equals 1/2 of 155 times 3.4 squared. Now let's see how much we get there. So when I solve this, what I find is that the kinetic energy, in this case, equals 5.9 joules. I'm going to leave the extra numbers in here. And then what I'm going to do is I'm going to say, well, this is how much energy I got when I push on the carpet. This is how much energy I put into it. So the missing energy is work. So what I do then is I just take this amount of energy here, 6750 joules of work was done on it, minus what I actually got in kinetic energy, which is here. So I'll say minus 895.9 joules, and that gives me 585 54.4 joules. And now I'm going to round this for significant figures, and it seems to me that I've got 2 here, I've got 2 here, I've got 2 here, I got 3 here. I'm going to round to 2 significant figures, and so what I get is 5900 joules of heat energy. Alright, number 9, we have a baseball applying newtons of force across a certain distance. So I sense a work equation coming on. How much energy does the bat transfer? I'm going to use the work equation. I'm going to say work equals force times distance. And let's see, the force is 1180 newtons times the distance is 1.2 meters, and therefore the amount of work that was done is 1416 joules. And it looks like I have to round it. In this case, I have 3 significant figures here, I have 2 significant figures here, so I have to round this number here to 2 significant figures. I'm going to round it to 1400 joules. Now, if I look at the next one, it says if the ball leaves the bat at 45 meters per second, what is the mass of the ball? So now I have velocity and mass. That's the kinetic energy equation. Kinetic energy is going to equal 1/2 mv squared. In this case, I'm looking for mass, so I have to know the other values. Well, it turns out I know what the kinetic energy is. I have an equation above. Now, in this case, I'm going to this may seem surprising. I'm going to use the non-rounded value here, and I'm just going to round my total answer here. So, here we go. I'm going to say 1416 equals half the mass, that's a half, times the velocity, 45 meters per second, squared. Now, when I do this, and what I'm going to find is that that 1/2 of the mass is equal to 1416 divided by 45 squared, which is 0.699. But keep in mind, that only equals half of the mass. So how do you undo taking half of something? Well, you multiply it by 2. So I'm going to multiply both sides by 2. And what I'm going to find then is that the mass in this case equals 1.3985 kilograms, but I'm going to limit myself to 2 significant figures, and I'm going to call that 1.4 kilograms equals the mass. Okay, the last one's the doozy. Here we go. You can do this. Alright, so what I'm looking for here is how fast is the car now going, and what I've been told is the mass of the car, the velocity of the car, and how much heat energy the brakes have produced, robbing the car of its original kinetic energy. So what I have to do first is figure out what is the kinetic energy of the car to begin with. Getting bored of this equation yet? Here we go. So the kinetic energy of the car is going to equal 1/2 of its mass, which is 680, times its velocity of 34 meters per second squared, and that gives me a kinetic energy to start out with of 393040 joules of kinetic energy. Now the car puts on the brakes, and when the car puts on the brakes, it generates this many joules of heat energy, and therefore it will have this many joules less kinetic energy. So I'm going to take this away from this to find out how much kinetic energy the car is left with. So I'm going to subtract 49000 joules from this to find out what I'm left with, and that gives me 344,040 joules of energy are left in the car. And now that I know what the energy of the car is, I can figure out how fast the car is going by using the kinetic energy again. So in this case, what I'm going to say is 344,040 equals 1/2 680
times velocity squared. That means, well, let's just do this. 344,040, and half of 680 is 340. So I had to divide both sides by 340. And that means that the square of the velocity is equal to 1011. And now the way you undo squaring something is you take the square root. And I'm going to take the square root of both sides. So if I take the square root of that, that gives me a velocity of the car now has is 31.81 meters per second. I'm going to round that to two significant figures, and that means the car is now going 32 meters per second. And that's a good thing, because the car at 32 meters per second is definitely going slower than it was at 34, so I know I did it right.